Hello everyone. So in the previous sessions, we have been discussing about the random variables. So let's revise a bit. So what random variable is? So I said in the random variables, if you are not concerned about the output of an experiment, you are performing an experiment and there you do not care what the outcome came, but you are worried about some other number. You are concerned about some other number. We took example of, let's suppose, dice and these coin flips. In the dice, you are, let's suppose, throwing a die twice, and then you are concerned about what is the sum of numbers you will get on the die. That is your concern. Then what you do, basically you do a mapping of this sample space. What are the sample space you have? Okay, there is a sample space and you do some mapping from this sample space to what's called as measurable space in mathematics, but usually I call it, mostly they are numbers. So some values you have. So in terms of this coin tosses, let's suppose you toss 3 coins. So the possible outcomes are 8 possible outcomes can be. So from head, head, head to tail, tail, tail. These are 8 possible outcomes. Okay, then we said a random variable can be thought like this: number of heads, number of heads. So the total value this can take is either 0 or 1 or 2 or 3. Okay, so then we mapped this. Okay, we mapped this total sample space or whole the sample space to these numbers 0, 1, 2 and 3. So we mapped this. Whatever mapping we defined here, that's called actually a random variable. So random variable can be thought as a function. So it's a function which takes this sample space and maps it to some what's called as measurable space. But here you sort of restrict yourself to the discussion on numbers. We'll have this sample space and we'll map these onto these numbers. Okay, so this was a brief discussion on the random variables I wanted to have so that everybody is on the same page. Then we saw that there are two types of random variables. So these random variables are of two types. The first I said is discrete random variable. Discrete random variable. And the second type of variable is continuous random variable. And we had a thorough discussion on what is the meaning of discrete. So it can be infinite also, but it should be countably infinite. By countably infinite, I told you that there should be a mapping between that set to the set of natural numbers. Then we call that as countably infinite set. We give an example. Let's suppose we have a discrete variable x. X can be number of flips or number of trials till first head appears. Okay, a random variable can be sum of numbers on 2 dice is greater than or equal to 7 or something like this. Okay, so these things you can count, and there may be infinite things. So if you see this number of flips, it can take us infinite flips also. Let's suppose if the coin is really biased, let's suppose there is only 0.0001 probability of getting a head, it will take large number of trials till we get to this. So it cannot be it can be infinite also, but it should be countably infinite. It should not be uncountably infinite like we have in real numbers. So in this continuous example, we took the example, let's suppose some random variable y can be height of a person. So you know that height can be a continuous variable because now it can take uncountably infinite values. As I said that between 0 and 1 there are uncountably infinite numbers. Okay, that's what this discrete random variables and continuous random variables are. So now I want to have a discussion after this. I want to have a discussion, why are these random variables important? Why do we care about them? That's the first thing I wanted to address so that everybody has clarity on these, and that's why we are introducing them. Now if you know random variables, we'll see why are they important. Okay, so now in terms of machine learning, if you see it, so in machine learning we have this data matrix. So what is the data matrix? So in which we had the data in terms of this the algorithm that you are implementing, k nearest neighbors, you are making a recommendation system. In that you have this users and items. Okay, and each of the feature of this user probably is like this. Let's suppose this is feature 1, feature 2, feature 3, feature 4, feature 5, feature 6. Okay, let's suppose this is corresponding to some item 1, item 2, item 3, item 4 and item 5, something like this. So if you see the data matrix, so each of the item has got certain features. For item 1 we have got features f1, f2, f3, f4, f5 and f6. So if these values are numerical, Okay, if this value is a numerical, this feature 1 can take, let's say for this item 1 it took value 2, and for this item 2 it took value 3. Okay, for this it took value again 2, it took value 1, it took value 0. So now these features, if you see, I told you that if they are numerical values, so they can be of two types. They can be of categorical features where you have categories. Okay, they can be categorical features. How many of you remember this? Features are divided into different categories. One of the thing is we can have categorical features, and then one feature can be and even in these categorical features we can just map them to numbers also. Then the second, this feature, let's suppose this F6 feature, it can be a real feature, it can take any real value. Okay, so now you can think of these features as random variables. So if we have a categorical feature, let's suppose which takes values a, b, c and d. Okay, now you can see this as a random variable x which takes these values a, b, c and d. Or let's suppose we have a feature seasons. I think we did this problem in one of the classes. Seasons, we had some sort of like 4 seasons we had, or maybe I think it was weather or something, weather. So we had 4 types of weathers. We had sunny, we had I think cloudy, maybe some other 2 types were there. Okay, some other 2 types. So now if you see that this can be treated as a random variable which takes these 4 values, sunny, cloudy and whatever the other 2 values were. So this is a random variable. So again in the continuous realm, let's suppose you are having a feature of heart rate of patients. Now heart rate can be again a categorical value. So it can, heart rate can take usually values from, let's suppose 0 is when a person is dead, and the maximum heart rate that I think is measured will be some 350 beats per minute. So it will take some finite values. Again, if we are having a data set which contains the records of patients, so there you will see this feature will take these values. The heart rate will basically take values from 0 to 350. Okay, the lowest value can be 0 when a person is dead, and 350 means when his heart is pumping the blood really fast, and this basically is happens when there is like some low blood pressure and there are problems with the heart. So it can happen, and usually the person has high chance of heart attack here. So now you can see that from values 0 to 350, these values again are taken by a variable, a feature. So in mathematical term, what we can see is this will be called as a random variable. How many of you understood this mapping? How many of you understood the mapping? Okay. So in this I'm saying that every feature, most of the times you can treat them as random variables. So what maths gives you, so why are we making such a big deal of this? Why we are making this as a big deal? Because now you can have any feature whatsoever it is, you can solve any problem. Now mathematics or the probability will give you the tools to treat these problems without even knowing about the problem. You will treat the problem and you will have a treatment, you will make a framework out of these, and then you will sort of have a set of tools which you can apply onto these features. Okay, now it doesn't matter to me whether you are using a problem, whether you are solving a problem related to recommend system, or it doesn't bother us if you are solving a problem which has something to do with the patient records or something. If you see this, each feature can be treated as a random variable. And now you can see that these follow mostly in 2 case of random variables. Either it can be categorical features, it will have some categories or finite values, so we'll call it a discrete random variable. Or it can be a continuous random variable where the values like this, we have suppose height of the people. So height of people can be of any precision. Let's suppose somebody is 171 centimeter, somebody can write 171.5 centimeter. Okay, this can take continuous values. So each the feature can be either treated as can be treated as discrete random variable or a continuous random variable. Everybody clear till this? That's why we introduced these random variables. Okay, so what we have a problem that we'll solve. Okay, now we need to find tools. This is what we are doing. So mathematics basically gives us tools. So every problem that follows this sort of, and most of the machine learning problems will be like this. There will be features, there will be some sort of label and things like that. So what if you are using a probabilistic algorithm where you use probability and these distributions? So it is better to just abstract out this problem and go into the mathematical details of the problem. That's why if you see our logistic regression, we wrote probability of x something given y. We did not care about what exact features were. We're just doing a treatment at the abstract level. So our goal was not to solve only that particular problem, but with that we solved a whole bunch of problems which sort of followed that framework. We have a problem, now we are abstracting out the problem, and now we are defining the tools. So one of the tools is this probability, and in probability we define the random variables. Okay, Coming back to the random variables again, I think you are now clear why do we use these random variables, why are they important. Each of the mathematical concept is important because it maps to some real world problem, and sometimes we lose the sight of that. Sometimes when you are dealing with the maths, you lose the sight of this real world problem, but it is important to keep those sights in your vision and in your view, and after that go into the mathematical details of these problems. And once you know all the details, then any type of problem which follows that framework, okay, you can easily solve that problem. Now we have these random variables. There are two types: discrete random variable and continuous random variables. Okay, so there are different types of these discrete random variables also. So probably we'll discuss them in the separate class. What are the different types? But why are they important? Now we define some properties regarding these random variables. So this discrete random variable, we had a discussion on this discrete random variable. Now you see that feature. Let's suppose we take an example in our machine learning setting. One feature can be treated as a discrete random variable. Now what is so important about this? Now I can sort of summarize these things. If I have some knowledge about a discrete random variable, okay, it's as if a problem fits into that framework, I know a lot of things about that thing. Okay, let's suppose I'll do a study of discrete random variables. Now you know that heart rate, let's suppose heart rate is a discrete random variable, and similarly we can say age of people is a discrete random variable. Similarly, let's suppose we are solving some other problem in KNN. Suppose the feature in the movies that we have, let's suppose the rating from 0 to 5 is a discrete random variable. So if I did some treatment on this, if I know how to treat this random variable, if I sort of built a framework by which I can understand this, so it means it's equivalent to understanding all of these together. That's what we'll be doing. So in this discrete random variable, I told there are different types of discrete random variables now. Why? Because they have different properties. Okay, I'll just name them and then we'll have a detailed discussion probably next class. So the first discrete random variable type is uniform random variable. Uniform random variable. Okay. Then we have Bernoulli random variable. Then we have binomial random variable. Geometric random variable is also there. Geometric random variable, and so on. There are a lot of random variables. But why do we study? You should be clear about this, because each of this they have a property. So they follow a property. So that based on that property, so if you have these features, it will fit one of these random variables. So if we do a study on this, okay, it is equivalent to that you know everything about that feature. Okay, that's why mathematicians have developed these frameworks. So just to give you an intuition what this uniform random variable is. So if you have a variable, if you have a random variable x which takes some values, let's suppose 0, 1, 2, 3 and 4, it takes these 5 values. If we do not have any knowledge, about this, so when we compute the probability mass function, we had a discussion on this probability mass function also in the previous class. So what you do not have any knowledge of how this mass should be distributed. So in that scenario, what you do is you say that each of this outcome, each of this value of the random variable basically is uniform. We do not know how much mass should be constant at each point. Then we make an assumption that we'll put the value as uniform. That's why it's called uniform. We'll give same value to every of these outcomes or each of these values that a random variable can take. So you can write it like this: P of x given x. So this is how probability mass function is written. Okay, probability this x takes the value x, or we write it like this: P of x takes the value x. This is the bigger x and this is the smaller x over here. Or also I give you a notation that this is something like the probability of those entities from the sample space. Okay, those entities from the sample space for which this x takes the value x. So this notation basically means if you have a sample space like this and you have a b c d, so which of these entities map to a value x. I think you also know that problem. Let's suppose you had this die, so in which we had the number of heads. So total possible were 8 outcomes like this, and you mapped this outcome to 0 number of heads. Then 3 outcomes were mapped to like 2, and these 3 were mapped to, let's suppose, some 3, and again I think one last was a map to 1. These are number of heads. Okay, how many of remember you? That's the notation. But usually we'll stick with this notation or this notation. Okay, and probably sometimes we'll write it like this: probability of x. So if we do not have different random variables, we'll just write the probability of x taking the value x is this. So this is probability mass function. So I'm discussing about the uniform random variables. Uniform random variable. We'll have a detailed treatment of them once we know about the properties. But just for the sake of completion, I wanted to cover these so that everybody is on the same page, and if you sort of follow any book or read them, and you will have an understanding of what these are. So what I'm saying is a random variable is uniform if you do not have any knowledge about what is the value that will be taken by the random variable. So I give an example. Let's suppose we have this x can take values 0, 1, 2, 3, and 4. So these are the 5 values x can take. Now I do not know anything about the probability mass function. Let's suppose for me all of these values are equally likely. I don't know which will happen. So when you describe the probability mass function of this, so what you will do is you will say probability of x takes the value I, whatever this I is basically equal to 1 divided by the number of elements. So here we have 5. This is 1 by 5. Okay. So if you plot this PMF, so this PMF will be something like this. So for value, this is value, let's suppose 0. This is value 1, this is value 2, 3, and 4. So each of the value will be uniform, somehow uniform. So for this, let's suppose this will be the value, and for this, again the same value will be there. Okay, something like this. So this will be the probability mass function. This basically is what is called as a distribution, how this mass is distributed. So you will probably sometimes hear it in the books written as distribution. So this is the distribution of a random variable. Okay, I hope that everybody is clear with the uniform random variables. Okay, this uniform random variable basically is when you do not have any knowledge, or you do not make you are not biased towards one value or towards other value. That many of the problems in real world, they follow this uniform distribution. Okay, when you perform a random experiment, so you say like x can be a value. What will be the output of the die? It can be 0. It can be 1, 2, 3, 4, 5, 6. 4, 5, 6. Now if you see that this die is a fat die, so there you will assume that each of these values will be equally likely. Then each of this value will be probability 1 by 6. That's why PMF will be somewhat like this. Okay, many other real world phenomena like tossing of a coin. Okay, there you will see that it is a if you say that it is either head or tail, so what's the probability there? So when you will assign the probability, you will say that each event is equally likely, and I can have that, I can represent that as a uniform random variable. Okay, then we have other variable that we wrote is, I think, Bernoulli random variable. Everybody clear till this? Any questions? So now we'll discuss Bernoulli random variable. Bernoulli random variable. So what I was discussing here is not the final, so we'll again touch these things, but for the sake of completion, I just wanted to tell you what these things are, and then we'll do a thorough analysis of these things. So what this Bernoulli random variable is, suppose you are doing an experiment. Okay, you are flipping a coin, you can be doing some experiment like that. If the experiment has only two things, if it has failure or success, okay, if it is an experiment where you have a failure or success, many of the real world phenomenon, like they follow this. Let's suppose you are tossing a coin. In that it will be head. Let's suppose head we'll call a success and tail we'll call a failure. Okay, then this we'll study under this Bernoulli random variable. And the first phenomenon I'll tell you is tossing of a coin. Tossing a coin. And other phenomenon can be, many phenomenon can be mapped to this. Let's suppose in Bangalore today it will rain or it will not rain. Again, there is success. Let's suppose is rain. There will be rain, and no success or failure means there will be no rain. So these are experiments. Okay, in these are experiments, we have, let's suppose, success has the probability, some success has probability p, and the failure obviously will be then 1 minus p. In these sort of trials, we come up with these what's called as Bernoulli random variables. Okay, we define this Bernoulli random variable as this x, which takes these values 0 and 1, or 1 or 0. So 1 means success and 0 means failure. And again, this p should be a probability function. This p over here. Sorry, something happened. Okay. Okay. So here what I'm saying is that this random variable only takes two values. It can take value 0 and it can take value 1. And many of the phenomena that you will see in the world, they do follow this failure or success. So in that we'll have this random variable taking values 1 and 0. Okay, this is what in nutshell a Bernoulli random variable means, a random variable which can take two values, and we have a notion of success or failure there. Okay, this is what a Bernoulli random variable is. It will take two values 0 and 1 with success with probability p, and this failure with probability 1 minus p. From this random variable we come to what's called as binomial random variable. Binomial random variable. So what this binomial random variable is? So if you see this Bernoulli random variable, it has only one thing that you have to know. You only know the probability of success. You can write this something like this, some Bernoulli B or Bernoulli of P. So if you only know this P, let's suppose somebody gave you this. So you are understanding by this that there is a random variable which takes two values, 0 and 1. So it takes the value 1 that in success with probability P. Only one parameter is needed to know about the Bernoulli random variable. If I say you, let's suppose falling of a rain, it follows, it is a Bernoulli process, let's suppose. And in that you assume that rain will, the probability of it, probably it will rain will be P, and probably it will not rain will be 1 minus P. You only want to know only this feature P. Okay. Then in this binomial random variable, what there is, now you do this n trials. Okay, here you were just doing one trial. So binomial random variable is nothing that you do n trial, and each trial here is a Bernoulli random variable. So you do n trials, and each trial is a Bernoulli random variable. That's what this binomial random variable is. We call it, also called this as binomial process. So why is it called binomial? Let's suppose we have even seen this. So we have even seen this. Let's suppose we have this number of heads. So if you have that process, and let's give it an example. Give example for this. So what I said is that there will be n trials, and then each trial will be a Bernoulli random variable. Now you know that in Bernoulli random variable, the only parameter that we wanted to know about is the probability of success. So now in here there will be two parameters. So binomial random variable will be something like n comma p. So n will be how many trials are you doing, and p means what is the probability of success. Okay, let's suppose example will be you are tossing a coin n times. This is what you are doing. You are tossing a coin n times. Now in this you wanted to have a function. You wanted to see what is the probability that, let's suppose I'll get number of heads will be I. So number of heads is equal to I. If you see that when you are tossing the coin once, it's a trial. So in this it can be either success or failure. So if a head appear, then it will be a success. If a tail appear, it will be a failure. Now each of the trial, if you see, is a Bernoulli random variable there. Now the whole process is a binomial, following a binomial process. It's a binomial random variable. So this number of heads is equal to I. So this is what I'm interested in. Okay, this is my random variable. So if you see this random variable, I'll call it as binomial random variable. Why? Because because I'm tossing a coin, and each of the tossing of coin is a trial, and each trial is a Bernoulli random variable. So I'll have some n trials, let's suppose. And what is the probability that the head will appear? Let's suppose it's p. Usually in a fair coin, p is 0.5. Okay, so this is a binomial process. So now if I say you, what is the probability that we'll have this number of heads is I. What is the probability of this? Okay, so it can be like this. So there will be different. Let me make it concrete. Let's suppose p of 2. This means what is the probability that I'll have two heads in n when I have n trials. Okay, I can have like this, head and head first, and all others are tails. Okay, so I can have head over here and rest are tails. I can have head over here and rest tails. There will be lot of things like this. So in these n slots, let's suppose we have these n slots. I just want two heads. I want head anywhere. Okay, and rest can be tails. So how many of such things are possible? How many such permutations are possible? Okay, how many of these are possible? So usually this is n choose 2, because now I am doing n of these combination. Only two place should be there where we're head. So these number of possibilities will be there. So if I say that I am doing probability, I am writing it like this. There's a binomial process, and then I am doing a flip, 5 times flip, and the probability of heads is p. Okay, now I have, these are my 5 tosses. Each of the toss now is a binomial, a Bernoulli random variable. So here the possibility is header tail, header tail, header tail. Now I want to see in these 5 tosses with this p. Okay, now I want my success is basically getting a head. Getting a head is my success. Okay, this is my success. Basically, if I got a head, that is success. If I got a tail, that is failure. If I only know these two, Like I'm tossing the coin, let's suppose 5 times. Okay, out of these, let's suppose I want now this probability, this p of p should be taken to, I want 2 times the head should be there. If it is if it's 2 times head, like I should be successful 2 times. So how to write this? So it can be somewhat like this. So head and head can be here, okay, and or head and head can be here. Let's suppose it can be head here, it can be head here. So how many number of possibilities are there? So we can write it 5, choose 2. So these number of possibilities there. And what is the probability of each this? Each of this is with probability p, and others will be with probability 1 minus p. Okay, that you can write. So 1 minus p. So 1 minus p, that you can write n minus I over here, or n minus 5. So 5 minus 2 over here is that. How many of you understood this? So in our case, we had these 3 experiments and we wanted heads to be 2. So binomial of, we are making 3 trials and with probability p, small p, and I want probability 1 head should appear. So how will 1 head appear? So 1 head will appear like this: head, tail, 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 head, tail, 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 head. So these are the 3 possibilities where 1 head will appear. Okay, so this basically is 3, choose 1. That's equal to 3. So now I'll write 3, choose 1 and multiplied by the probability p, and for other tosses it will be failure, that is 3 minus 1, that's n minus I. So in general I'll write it like this: if I want probability of I, okay, if I want the Bernoulli random variable should take value I. So for Bernoulli for this binomial random variable, sorry, so I'll have number of trials, that is n, comma, and I'll have the probability p, probability of success. So how I can write this? Probability of I is equal to, I'll have n choose I, these many number of success will be there with probability p, and multiplied by 1 minus p, and others will be this n minus I. So this is the formula that will follow. So how many of you understood this? Everybody understood this? Okay, so in nutshell, we have a Bernoulli random process or Bernoulli random variable which takes values 0 and 1. So 0 means failure, 1 means success. So it takes it with a probability p. Okay, we only need one parameter, that is, so Bernoulli is written like this: Bernoulli of p. That means success is p. So if you have tried binomial, so binomial is written like this. So n means number of trials, and with the success, what is the success rate of each in each the trial? What is the probability of success? So we write it like this. Okay, we'll have a detailed discussion on these things, but I want you to know the definitions at least. So we saw what a Bernoulli random variable is, and then we saw what a binomial random variable is, and then before that we saw what a uniform random variable is. I hope that everything is clear. Now we again have one more random variable, that's called a geometric random variable. So that I'll write here. So geometric random variable. Again, do not lose the sight that these random variables studying, because in machine learning each feature can be treated as a random variable. Okay, so that's what we are doing. So we are not doing it just for the sake of mathematics. We are doing it because we want to map our problems to this, and once we know about these random variables, so what will happen there is, so we can sort of map different sort of problems where we have different data metrics, where we have different features. We can have the same treatment for these, because each of the feature is considered as the random variable now, and each of the feature can be of different category. It can be, let's suppose, if you see in here, if you see this this Bernoulli random variable, sex male or female, 0, 1 values, so it can be treated as a Bernoulli random variable. Uniform random variable, let's suppose you are doing some trial and then you have no information about that, you can take that feature as a uniform random variable. And again, there is a geometric random variable. We have also discussed this geometric variable. I just am now giving the name to these concepts that you have learned. So we have done an experiment where I said we are doing n tosses of n tosses. So for a coin, we are flipping the n times. So we want to see, so how many tosses will it take till the first head. So number of tosses till first head appears. Okay, this sort of process is called a geometric process. Okay, why is it called a geometric process? Because you can see that we are taking these n tosses. The values can be either, so even let's suppose we in the first toss itself we got this. So in the first toss we got the head, or in the second toss we got, this means we'll get this head only. So in here we'll get first tail then head. Okay, in the third toss sometimes we'll get it. So this is tail and head. Okay, this sort of process is called actually a geometric process. So in that, what we have, the experiment is where in infinitely many independent tosses of a coin. So let's suppose the experiment could be infinitely many independent tosses tosses of a coin. Okay, and again the probability of head will be given to us, probability of head, because we care about this probability of head is equally. Then what is the sample space here? Sample space is set of infinite sequences, so this will be sample space. So sample space, if you see over here, is sequence of head and tails. This is our sample space. Now what are we interested in? So our random variable in here. So if I introduce this random variable, so this will be number of tosses. Oh, sorry. This will be number of tosses till first head appears. Okay, so this sort of process will be modeled by this geometric random variable. Okay, and other phenomena also follow this. Why? Let's suppose waiting time. So you are waiting for a train to arrive. There it also follows this geometric process. Okay, I hope that you got this notion clear. So what is the meaning of the geometric random variable? Is it clear? Okay, so I think we also solved this problem. We also solved this problem. So we said that this value, this can be taken as value 1, 2, 3 up till n. Okay, so we said if this is random variable x, so it takes some value, let's suppose k. So what is the probability of that? So the probability of that is for the first initial k minus 1, it should be a failure. So it should be 1 minus p raised power k minus 1, and at the end we should get this probability p. So this is how we compute the probability over there. Okay, so how many problems are fit in this model? There are infinitely many problems that fit into that model. I just gave an example of number of trials of until a success appears. So number of trials till a success is seen. Let's suppose you can see, like, you can model even your study like this. You can say how many days will be passed till I get the job. Again, you can model this problem by using this geometric random variable. Okay, number of trials till the successes. Okay, or maybe the second thing can be waiting time. Till what time do I have to wait till the train arrive? And something this can also be modeled by using the geometric random variable. So it'll be like something like this. So you will see its PMF like this. Okay, so in terms of, let's suppose you have this tossing of coin till the first head appears. So you will see that it with high probability you will get this one, and then slowly it will decrease. Okay, slowly it will decrease. For example, for many other tosses you will get the head on the first toss, and slowly it will decrease. With p, this will be again, then for the second toss it will be 1 minus p into p, and this will be 1 minus p square into p, something like this. Okay, and slowly it will decrease till this number, let's suppose k appears, 1 to k. Okay, that's why if you see, it follows some geometric progression sort of thing. That's why it's called a geometric random variable. So we saw different types of random variables. So first we saw random variable. So in that we had two types. We had discrete and we had continuous. So in the discrete setting, we saw, I think, 4 random variables. So we saw a uniform random variable, then we saw Bernoulli random variable, then we saw binomial random variable, and at the end we saw geometric random variable. And there are a lot more to cover. Okay, probably we'll cover some of them, but I hope that at least you got some notion of these 4 random variables. Okay, and we also saw what is the PMF. PMF is nothing, a function which distributes the mass. Okay, if you have value 1, so we distribute this to the values of this random variables. Now comes the really important topic. Why was I covering this sort of detail, these many details? Because I told you that these random variables, we can just have some metrics, some stats. Okay, we can have very few statistics. Okay, by the help of which we can easily know about a random variable. Okay, the first stats can be thought as mean value, and second thing can be thought as spread. Now we'll also name them. I think in one of the previous classes I told you that we'll have a detailed discussion on this mean and spread. Okay, now let's suppose I have a random variable x, which is a discrete random variable. It can be of any type. Now I don't care about the type, so it will take a lot of values. Let's suppose it takes k values. Now I want to see the central tendency. Where is the central tendency of this variable? What is the mean value of this? Okay, that will give me some idea about, okay, how, like, what value to expect. Okay, that's why sometimes this mean value, this is usually defined for the population. Let's first make a small digression. I'll define what a population means. There's a difference between population and sample. I think I might have covered it in some lecture, but again I want to just discuss for the sake of completion. So usually you have data. Okay, you will have a lot of data that will be given to you. You have to feed that into machine learning, and we say that this data comes from some data distribution. Basically, some random variable explains it. Okay, it can be either, let's suppose, in terms of the discrete random, it can be uniform. It may be coming from a uniform random variable, or it may be coming from a geometric random variable. When we learn about the continuous random variables, we'll see that there are something called as Gaussian random variables. Okay, or Gaussian process, Gaussian distribution. Basically, what we say that this data comes from a distribution that we do not know. Okay, so what population means that if you have access to all the data, okay, let's suppose I want to compute the height of a human being. Okay, height basically follows what's called as a bell curve. We'll see that it follows a Gaussian distribution. Okay, if I have to compute this height, basically, if I know all the human beings, if I take all of these human beings that are on the planet Earth, okay, all the human beings, so I can tell you what is the mean value there. So I can just take, let's suppose we have n number of people on the planet Earth. So somehow there's a technique by which I can know everybody's height. So what I'll do is I'll just sum over all the heights. Let's suppose xi is the height. Okay, I goes from 1 to n and divide by n. So this will be the average height of a person on the planet. Okay, and similarly, let's suppose this is called as population. So population means when you have access to whole the data. So whatever you are doing is you have access to that. But in the real world phenomenon, you don't have access to the whole data. Let's suppose weather. So whether you don't have access to all the data that is there. So you have access to a small subset of the data. That subset basically is called a sample. So what is population now? So population means the whole data, the whole thing. The whole thing. Okay. So what is a sample? Sample is some subset which represents data, which represents the population. Okay, let's suppose now you have to see you are making a drug. Let's suppose, for instance, you are a medical professional where you are developing new drugs for diseases. Now you cannot do the experiments on all the people on the planet. Let's suppose some 100,000 people have that disease. Okay, 100,000 people have a certain disease. Now you are making a drug. So it is foolish even to consider I'll get all of these people and I'll get my experiment done on all these people. So better what we do is basically we'll take sample from this. I have given an example, I think previously somewhere. So whole the blood is our population, and if you take a sample of the blood, that is called a sample. Why it is called a sample? Because it's a subset of the blood, and it has all the same properties which this population has. Okay, samples should not be different from the population. Otherwise, we won't be getting the good results. So sample should be, that's what I wrote here. It should be a representative of the population. It should represent the population. Okay, your blood. Let's suppose you take 1 pint of blood out of your body, or maybe some milliliters. Let's suppose 5 milliliters out of your body. This 5 milliliter, what are the properties this 5 milliliters have? All the blood in your body has the same property. Okay, let's suppose pH value of your blood is somewhere around like 7.2 or something. It's in basic nature. So 7.2 is the pH value. So if you see the whole blood, it will have the pH value of this. If you take only this 5 ml of blood, it will again have the same property. Okay, again when you compute these, when you go to this CBC reports, or maybe the whole basically you did the blood test. So in that they'll just take a sample and they'll say these many number of cells you have in the body, probably you lack lymphocytes, you have less platelets and these things. They do not check the whole blood in your body, but what they do is they'll take a sample of your blood, and the sample basically represents whole of your blood. Okay, then based on that they perform the calculations and they say something about the population. Sample is a subset which represents. The sample can be sometimes very different from the population. Then it makes problem very difficult to solve. Let's suppose your blood was taken such a way that it was way thicker at a place. Let's suppose what happened is you had a cut somewhere. So when you had a cut somewhere, so you took blood from there. So now the platelet count at that point will be very high, because the platelet count at the other body parts will be less, because now you got the cut on the body. Because of that cut, what happened? The whole of this platelets came to sort of heal that whatever the cut there was. But if you take the blood from there, now it is not representative of the population. Okay, that's why usually they do not take blood from the wounded patient. So if a patient is wounded, and then blood may be like it may not be homogeneous. Now there will be different properties there. That's why they usually see they'll take blood. Okay, was the blood taken from this let's suppose arm? So if you say yes, they probably will take the blood from next arm. So if the guy knows probability, he knows what he's talking about. He knows that basically the sample should be representative of the population. How many of you understood this discussion? What is the difference between population and what's the difference between sample? Whole of the machine learning is a tussle between this, because we do not know this population, and maybe if we know, but we do not have access to this population. So if you have access to this population, you know the probability distribution it came from, you know the distribution this came from. But what we have is, we have just some samples, we have some data points. If you have these data points, then you have to somehow make an assumption that this sample represents some population. That's why most of the times I'll write this x comes from some probability distribution. I'll write it something like this. Okay, and then we'll say I do not have access to this probability distribution. What I'll have is, I'll have access to samples. So based on these samples, I'll have to somehow guess this probability distribution. So this is the probability distribution it comes from. Okay, so this is the discussion I wanted to have before explaining this few slides. We have this mean and spread now. So why do I care about these things? So now there is something called as population mean. Population mean basically means, if I have all the data, let's suppose if I have a data and then I compute the mean, that mean will be population mean. That will be the exact mean. So mean gives us central tendency. So what is the central tendency? Okay, and if you see what is the average height of let's suppose an Indian person, so it is nearly, I think, 5.5 feet 4 inches or something like that. So what is the central tendency? So that is given by the mean. Now you do not have access to all of this population. Okay, so what we do is, we'll introduce a concept called as expectation. Now you know that you can only compute mean usually if you have access to all the data, if you have access to all the things, and you can put them together and just compute the mean. Now in order to do this, so what probability gives us, basically it gives us tools to compute this mean. So expectation is somewhat a mean. So if it's mean for the whole population, if you know all the population, that's how I can define this. So expectation, basically what is the expected value? So that's what standard tendency is. So this is some sort of average value, but for the population. Okay, now we do not compute the mean directly. So what we do is, basically we won't compute the mean. So we'll compute this expectation. That's why we call it expected value. So what is the expected value? So this is the concept related to this mean. So that we have seen this and this. So each of this random variable will have a mean, will have an expected value. Okay, they'll have an expectation. Okay, and they'll have a spread. So in this spread will be called as variance, and we'll see that also. And now we'll have the discussion on this expectation. How many of you are clear at least what expectation means? Okay, and why do we care about these things? Why do we care about this? Because I told you that we do not have access to probability distribution. That the thing that we have access to is some of the samples. Let's suppose we'll have a game. Let's suppose we have a random variable x. This random variable x is basically the amount of money you can win. Okay, the amount of money you can win. It can be, let's suppose you lose some dollar. Let's suppose -1 with a probability, let's say 1/10, and you win $2 with probability, say again, say 2/10, something like this, and you win $4 with probability 3 by this is now 10. I'll have to compute 213. This is 7/10. Okay, now tell me the expected earnings. Let's suppose you are in the stock market. So you are saying I lose $1 with probability 1/10. Okay, these are the values usually what will happen. Either I'll lose $1, or on the day I'll earn $2, or I'll earn $4. Maybe let's restrict our discussion to only 3 values. Let's suppose these are the only 3 things that happen in the stock market. The one thing is that you'll either lose $1, or you'll earn $2, or you'll earn $4. So the corresponding probability is given to that. So should you invest in the stock market by seeing this? Because this is the sample that you saw. Okay, you are saying yes, and can you give the mathematical description why should you invest?
Sir, mathematics तो नहीं पता, but like profit is to loss का ratio मतलब बहुत
Yeah, that's basically what mathematics is. Now we'll see what is the expected earning. So expected earning is, I'll have this -1, I lose this with probability 1/10. Okay, and plus I'll win this 2 with probability 2/10, plus I'll earn these $4 with probability 7/10. Okay, and you will get some value out of this. And now you can see that this is greater than equal to 0. Not equal to 0 either, this is greater than 0. This is overall profit. So whatever the value you got from here is called as expected earning. So you saw a whole lot of data, and then you figured out that these are the only values which will happen. Or maybe probably if you are playing a game, if you are going, let's suppose to some casino, and there you are playing a game where they are saying you these rules, and then you can sort of calculate the expected earning. You are saying that I lose this $1 with this probability. Okay, then I'll multiply this. So this is my total. How much can I lose? Okay, and then I can earn $2 with the probability 2 by 10. You'll just multiply these two things together and then sum up all these things, and then you will get the expected earning. That's what expectation is. Okay, so again, like making this a realistic game, that is mentioned I think in Schillen and Ross. So this is 1, 2 and 4. This is your earnings. So this is 2 by 10 with probably 2 by 10, and this is 5 by 10, and this is 3 by 10. So the game is like this. You play this game 1000 times. Now you'll have to do the calculations. You play this game 1000 times. What is the expected gain? What is the expected gain? Can you calculate this? Zakir, can you help me in calculation of this? So out of these 1000 games, so how many times will I win? So 2 by 10 basically means 0.2. So 0.2 multiplied by 1000. So these many times I'll earn $1. Isn't it fair? So these many number of, so in the 1000 experiments, I'll earn this many number of times. Okay, plus. And then with this is 0.5. With 0.5 probability, I'll win these $2 in the 1000 experiments. Okay, plus 0.3 times I'll earn $4 in these 1000 experiments. The divided by the total number of experiments. I want to see the average winning. What I'll do. Okay, at average, what is the expectation I'll get. Okay, now you see this basically is what we discussed in the previous in this previous expected earning. So this 100 will get just cancelled out, so you will just get this 1 multiplied by 0.2, that is 2 by 10, plus 2 multiplied by 5 by 10, plus 4 multiplied by 3 by 10. So this is the expected earning that you will have. How many of you are clear with this? What is the meaning of like expectation you got? So I can write expectation like this now. So expectation is some sort of average. Okay, so if I have to write an expectation, so how I can write expectation mathematically? So expectation is basically, it is nothing but some sort of average when you do not have access to the whole population. But what you have access to, you have the access to probability mass function. Now you have a variable and you have access to the probability mass function. So how to do that is like this. So this is expectation of random variable x. This is how usually it is written. Okay, and then each the random variable will take some values. Okay, it will take some values. Let's suppose some xi. Should I write xi? Okay, let's write xi. It will take some value xi. So xi multiplied by this probability, this x takes this value xi. This I goes from 1 to, let's suppose, n, if it takes n values. So this over here is the expression for expectation. You see how these ideas are very simple. They are really simple. But the only thing that we are doing here is introducing some more symbols, and then what are doing, manipulating the symbols, and then it's easy for us to even read these equations and then manipulate these equations. That is only the maths gives you. Basically math does nothing, it explains the reality. But why are people scared of this? Because they don't understand these symbols. So it is better you understand these symbols. So how many of you understood this formula now? Is it difficult?
No, sir.
So it's really easy. This is just an expectation. So basically we have this probability mass function. This function basically it will take the output of random variable, assign it a probability score, assign it some probability. Then we have that actual value. So this is some sort of average. So if we had access to all the data points in the world, then this will be exactly equal to average. But now you know that I do not have access to all the data points. So I have this probability mass function and this, then I'll create an expectation. I'll just have an expected value. Okay, I hope that this expected value is clear, and we'll have a lot of discussion on this expected value. So probably I'll give you a question which we'll solve. Okay, that will be the last thing that we'll discuss, and we'll take this expectation in the next class again. So the question goes like this. Okay, so you're contesting in a quiz show in which there are two questions. There is question 1 and question 2. Think about those questions. So you are going to a quiz show, and there you will be asked two questions, question 1 and question 2 you'll be asked. Okay, so you have the thing that you have decided is what question should I attempt first, or which question should I attempt first, which question should I attempt first. That is what you have to figure out. And now the details, I'll give the more details. Let's suppose even you are sitting in an exam and there are 5 questions. Okay, and then which question should you attempt first so that you get the maximum benefit. Similarly, if you are sitting in an exam or you are going to a quiz show where you ask two questions, you ask question 1 and question 2. So now both the questions are asked simultaneously. There's a paper in front of you, and now you have to see which question should I attempt first, so as to get the maximum gain. So the setting is like this now. Now, if you decide to try question I first, let's suppose the I is 1 or 2, I is equal to 1 or 2. If you decide to do this question 1 or question 2 first, that is, if you decide to do question I first, then only you will be allowed to go to the next question. So okay, if you just, let's suppose took the first question and it was wrong, you won't be allowed to go to the second question. So if you took the second question, then only you will be allowed to go to the first question. Okay, the game is like this. So they basically, if you decide to try the question I, and then you are only allowed to go to the question next question. So if the answer to the question is correct, then only you can do this. Okay, if the initial answer is incorrect, then you won't be allowed to do this. Now the contestant, whatever, let's suppose you are going there, so you will receive VI dollars. So you will receive these many dollars if you answer the correct question correctly. So VI can be, you will receive V1 if you answer the first question correctly, and you will receive V2 if you answer the second question correctly. So these many dollars you will receive. Okay, so if you let's suppose the winning that you can get is 0, because probably you whatever question you answered is wrong, and you won't be allowed to go to the next question. Or you can get V1, or you can get V2, or you can get V1 plus V2. Okay, these are the 4 possible outcomes. These are 4 possible dollars that you will win, or maybe these are the this is the money that you can win, money you can earn. Okay, so now the thing is, what order should be, what order of the question, what is the order that you should answer these questions with? Okay, that's the question. Let's suppose I'll give one more the probability I have to define is the probability that you know the answer for question I is Pi. So with probability P1 you know the answer 1, with probability P2 you know the answer P2, and let's suppose P1, and you can give the values to the, I'm making the question generic. So how many of you understood the question? These are the only details. The question is that you are going to a game show and there are 2 questions, question 1 and question 2. Now if you answered the question correctly, you will only be then allowed to move to the next question. Otherwise you will be, the game will be halted. So what now you have to do is, the question that you have to do is, which question should you answer first? So the first question you know with probability P1, and the second question you know is with probability P2. And the one more thing is given, if you answer the first question correctly, okay, then you will get V1 of V1 dollars or V1 rupees. And if you answer second question correctly, then you will get V2 dollars. Okay, in here, if you see the earnings can be 0 because the first question that you attempted, you gave the wrong answer. So in that, what happens is you won't be allowed to take the next question, then you earn $0. If you took the first question first and then you made the right answer, that you gave the right answer, so that you will get V1, and in the next, when you are giving the answer to V2, you basically get the wrong answer. So that in this setting you will only get V1. So if you decide to take question second first, you will win V2 if you answer it correctly, and after that maybe you answered the first question wrong, then you will get only V2. Or otherwise, if you took any question first and you correctly answered both of these questions, then it will be V1 plus V2. Now what is the probability that you will get this 0 answer? Let's suppose if you choose the first one first, then you will get it with probability P1 minus P1 if you got that wrong. Okay, I am just making this setting. If you chose to answer the first question, first, so this 0 will be, you will get with probability 1 minus P1. So this you will get probability with probability P1 because you got the first question right, and then you got the second question wrong. Okay, with this probability. So when you will get this V2? So this won't happen because you have decided to answer the first question first. And when will this happen? So this will happen with probability P1, P2. And similarly, you have to analyze the second case also. If you chose to give the answer second time, then you will compute the expectation, and you will see which expectation is more than other expectation, and you will see which your expectation is greater. You will decide that order. How many of you understood this question? If you have not understood this question, please watch this last portion again so that you understand the question and you see why is this expectation really important. And sometimes we have to take decisions based on this. Okay, what should be the expected value? Should I even play this game? Should I even invest in stock market? What will be the expected return? Okay, and should I even study? What will be the expected gain for me if I study this thing? So all these problems can be modeled in this probability realm, while you will have some distribution, and after the distribution you will make an analysis, and then you will get an expected value based on that. Okay, so I'll stop recording over here, and if you have any questions, I'll be willing to take them.